All right, today we're opening a case file on one of the deepest, most mind-bending mysteries in all of physics. It's called the black hole information paradox. So get ready, because you and we're about to become cosmic detectives.
And let's start with our first clue. Now, this quote, I know, it sounds like something straight out of science fiction. But trust me, this idea from physicist Leonard Susskind is absolutely central to our investigation. It might just be the key that unlocks this whole mystery.
You know, every great detective story starts with some kind of conflict, a real clash, and our story is no different. We've got a clash of titans, the two absolute pillars of modern physics, and the scene of the crime, you guessed it, a black hole.
So, in one corner, you've got general relativity. This is Einstein's masterpiece, the undisputed king of the very, very large. It describes gravity, planets, galaxies, the whole cosmic dance. And in the other corner, we have quantum mechanics, the ruler of the incredibly small, particles, atoms, all that weird quantum fuzziness. Here's the thing. Both of these theories work perfectly in their own domains. They weren't really supposed to ever cross paths.
Except they do meet. A black hole is the one place in the entire universe where their jurisdictions overlap. You've got an insane amount of gravity, that's general relativity stuff, but it's all crushed down into an infinitesimally small point, and that's quantum territory. It's the ultimate showdown. And when you force these two great theories to describe the same event, well, they give completely different answers. Their stories just don't add up.
And the whole conflict, the heart of the paradox, really comes down to one thing: the fate of information. Now, when a physicist says information, they don't just mean, ones and zeros. They mean the fundamental blueprint of a thing. It's the complete, unique quantum description of every single particle, its position, its spin, everything. It's the very thing that makes a book and not, say, a teacup.
And this brings us to a really important unbreakable rule, a central law of quantum mechanics. It's called unitarity. Basically says that information can never be destroyed, ever. You can scramble it up, you can hide it, you can rearrange it, but you can't erase it from existence. It's one of the most sacred principles in all of physics.
Okay, so let's recap the case file. We have our victim, information. We have a sacred law that says it cannot be murdered. And now let's introduce our prime suspect, the black hole. The big question is, does a black hole commit the perfect crime?
So here's how the crime supposedly goes down, step by step. First, imagine we take an object, like a book, with all its unique information, and we toss it into a black hole. It crosses the point of no return, the event horizon. Gone. Step 2, a huge breakthrough from Stephen Hawking himself showed us that black holes aren't actually black, they glow. They slowly evaporate over time by leaking something called Hawking radiation. And eventually, after an almost unimaginable amount of time, the black hole radiates itself away completely. Poof, it's gone.
And this is the smoking gun. This is the heart of the paradox. Hawking's original math showed that this radiation coming out is, well, it's completely random. It's thermal. It's a featureless, chaotic hiss of particles that tells you nothing about what fell in. It only knows about the black hole's total mass, its spin, and its charge, not about the chapters of the book or the color of its cover. The information, it seems, has been totally wiped clean.
So that leaves us with the million-dollar question, right? The central mystery of our whole detective story. If the black hole is gone and the radiation it left behind is totally scrambled and random, where did the information from our book go? According to Hawking's first pass at this, it was just gone, destroyed, which, remember, violates that sacred, unbreakable law of quantum mechanics.
For decades, this puzzle drove physicists absolutely crazy. It felt like a dead end. It seemed like one of our two best theories of the universe had to be wrong. But then we got our first big break in the case. A crucial clue that suggested maybe, just maybe, the information wasn't lost after all.
This first big lead came from a physicist named Don Page, who was actually one of Hawking's former students. He basically flipped the problem on its head. He said, look, let's just assume quantum mechanics is right. Let's assume information is saved. What would that imply? And his conclusion was that the Hawking radiation couldn't be random. It just couldn't. It had to, somehow, be carrying that information out.
And this idea led to something called the Page curve. Now, you can think of the Page curve as the fingerprint evidence we needed to find. It's a graph that predicts what the randomness, or entropy, of the radiation should look like over the black hole's lifetime. At first, as the black hole spits out radiation, the randomness goes up and up and up.
But, and here's the kicker, once the black hole has evaporated about halfway, that curve has to turn around and start dropping back down to zero. That downward slope is the smoking gun. It's the telltale sign that the radiation isn't random at all. It's carrying information out in a very specific, correlated way.
You know, the stakes here were so incredibly high that physicists started calling this whole debate the Black Hole War. And it even led to a famous bet in 1997. Stephen Hawking and Kip Thorne bet against another physicist, John Preskill, saying information was definitely lost forever. Well, fast forward to 2004, and Hawking publicly admitted he was wrong. He conceded the bet, and he paid up with a baseball encyclopedia, which is pretty fitting, right? A prize all about retrieving information.
So, Hawking concedes, the scientific consensus shifts, and everyone starts to agree, okay, the information probably does get out. But that just leads to an even bigger question. How? How does it escape the clutches of a black hole? The answer, or at least the beginning of one, came from a completely radical, mind-bending idea that turned everything we thought we knew on its head.
And that idea is the holographic principle. Yeah, you heard that right, holographic. It's this wild theory that suggests our 3D world might be something of an illusion. The core idea is that all the information needed to describe a three-dimensional space, like the room you're in right now, is actually encoded on its two-dimensional boundary, its surface. Kind of like how a 3D image is stored on a 2D holographic plate.
Now think about what this means for a black hole. It's just stunning. You would naturally think that how much information a black hole can store depends on its volume, how big it is on the inside. But the holographic principle says, nope, it's all about the surface area of its event horizon. The information isn't falling into some bottomless pit, it's being painted onto the surface.
And just like that, we have a potential solution to our crime. The book's information never truly gets lost inside the black hole to be destroyed at the singularity. Instead, it gets imprinted onto the 2D surface of the event horizon. Then, as the black hole slowly evaporates, that Hawking radiation picks up the information from the surface and carries it away, piece by tiny piece. The information is saved. Case closed. Almost. Okay, so we're pretty sure the information gets out. We've established motive and opportunity. But the case isn't completely closed. The new mystery is, what's the exact escape plan? What's the mechanism? So let's bring in our lineup of the usual theoretical suspect.
All right, we've got a few main contenders. First up is the small corrections theory. This one says Hawking was basically right. He just missed some incredibly subtle quantum connections in the radiation that secretly carry the information out. Then there's the fuzzball idea, which comes from string theory. It suggests a black hole doesn't have a sharp edge at all. It's more like a giant fuzzy ball of strings, and the information just stays on its surface. And then you have the really dramatic one, the firewall theory. This proposes a literal wall of high-energy fire at the event horizon that would incinerate anything trying to get in, just to protect the purity of the information. I mean, this is an incredibly active field of research right now. Physicists are deep in the weeds, using super advanced concepts from string theory, things like brain systems, to try and build a microscopic model of a black hole. They're trying to figure out exactly how it stores and releases information, hoping to find that one piece of evidence that points to which of these suspects is the real culprit. So, that's pretty much where the case stands today. We haven't pinned down the exact how just yet, we haven't convicted a single theory, but the verdict on the main charge is in. Information is not lost. Black holes are not the perfect criminals we thought they were. That sacred law of quantum mechanics, it seems to be safe.
But you know how these things go. Solving one mystery just opens up another, even bigger one. The holographic principle might have saved the day by explaining a black hole, but it leaves us with this absolutely profound, lingering question. If a black hole can be a hologram, could our entire universe be one too? Is it possible that everything we see, everything we experience in 3 dimensions, is really just a projection of information written on some distant, 2-dimensional cosmic boundary? Now that is a case that is far from closed.